Let's take a look at the execution model of the GPU. So the very basic unit of execution is a thread of execution, or simply a thread. And this is a piece of code that can run independently. Now, the whole point of GPUs is that you have lots and lots of these threads. And in the CUDA execution model, threads are organized into thread blocks. A thread block is just a couple of threads grouped together for purposes of organization. And when you fire off your kernel, you can actually have several thread blocks. So here is another one. Now, thread blocks are defined in yet another arrangement called the grid. So ultimately, when you fire up the kernel, you use those funny angle brackets to specify the dimensions of the grid of thread blocks plus the number of threads that each block contains. So for example, the illustration here has 2 blocks of 3 threads, so we would call it as do something 2, 3. And here is a different arrangement. This time I have 4 blocks of 2 threads, so we would define the kernel call as do something else with 4, 2. So thread blocks that you feed CUDA are actually scheduled to run on available streaming multiprocessors. And you don't have any control over which particular SM a thread block runs on. It's typically the scheduler that takes care of the decision for you. What happens is that each SM executes 1 block at a time, but it's not exactly as simple as that. Actually, each thread block is subdivided into warps. And each warp has a certain number of threads that is once again predicated by the compute capability of the device. And you can consult the variable warp size to find out what the size of the warp is on your device. Now, the warps of a thread block are handled concurrently. And if a warp gets stuck on some memory access, the scheduler can actually take another warp to execute. And the CUDA Warp Watch, which we have already seen, helps us visualize variables and expressions across the entire CUDA warp.